So my name is Vesa, Jääskö. So I'm representing our teamwork. We come from Aalto University. We are still in research to business mode at the university, but we are hopefully entering to commercial mode after this year. We are having a project in which our main targets are to be able to prove our technology, to prove the technology readiness, find the business logic, how to get into the market, and then also to find the first minimal viable product. And that's one reason why we are here discussing all interest group, the builders, the architects, glass processors, float glass manufacturers, in order to understand that what our business model would then be when we are entering into market. Here's our team. It is divided in two parts. Like in front here you can see Gufran Hashmi. He's actually the genius behind this technology. He has been developing this perovskite-based solar cell technology for a couple of years, and he assisted with Taina. And then there's Sasan and me, and we are responsible for the commercializations and the business of the future company. My background is actually in industrial design, and I've been in charge for developing and identifying and developing the actual product solutions and what would be the business area that we are entering in. So as I'm not that deep into the actual technology, and because we see that this perovskite-based technology interests very much the audience, we have Gufran here in front here, that if there are questions in relation to technology, so I can bounce those to Gufran and he can directly answer those. But then why perovskite-based solar cell technology? We have overcome the most tricky issues in relation to durability and stability issues, so that we have that kind of configuration that enables us to create commercial viable BIPV solutions that have good performance. It seems that our technology is quite well also in indirect lighting condition, which is really important as we are dealing with BIPV solutions. The product structure is integrated in that sense that all the qualities that are needed for commercial viable BIPV product is there. We don't need to have any extra coatings or layers in order to have that kind of solution that architects would like to utilize in architecture. As we see that one of the gatekeepers in get this BIPV a bigger business is actually that there are not that good solutions on the market at the moment that architects would like to use those. And yes, since the cells are printed, we can basically have any shape in this pattern of cells that are printed on glass. So if we go and see the product structure, we have FTO-coated glass in order to have the electricity conductivity that we laser scribe in order to have the areas, the conductivity accordingly with the cell areas to control the electricity conductivity. And we simply print with screen printing and inkjet printing methods enhanced with heat treatments, the active cells on top of each other so that they actually form the performing cell. The cell itself is quite fragile, and therefore we need to encapsulate it in order to make a feasible functional product. We are integrating the tempering in the manufacturing process so that the end product is always tempered. We need tempering because the thermal stress and the difference between the black, the printed area and the clear area is so high that the tempering is needed. In laminated glass solutions, our product structure is very similar. There's just this EVA film or other material. We are studying also that what is the most feasible manufacturing method and material for bonding two glasses together. So, as the active cell layers are printed, they form black areas that can vary in size and shape in order to be able to allow architects and designers to develop those kind of patterns that can be integrated into architecture. The cells are serially connected together, and we are aiming that kind of outlook that the silver lines that are connecting the cells would be invisible to almost invisible, and we have just the silver connectors on both sides of the glass. We have divided our product solutions in three main application areas. We call this kind of see-through solutions pattern PV glazing that can be used in curtain walls, skylight, canopies, and for instance balustrades. Then we see that this kind of semi-transparent solution is needed also, so that only when we are controlling the amount of light that is getting through inside the building. And then third application area where the actual product is opaque, not see-through, so that actually it can be attached on any other building envelope area than the window or see-through area. So here you can see example of the pattern PV glazing in curtain wall, so that the first glass of this insulated glass unit has our technology. So in many cases in architecture the printed glass is utilized in order to prevent all the direct radiation come inside the building. So now we can have the same pattern functionality and the electricity harvesting in the same product. We are generating semi-transparent glazing so that we are printing, let's say, 2 mm wide cell stripes, and depending on the proximity you can then change the see-through grade, and of course affect on the performance of the cell itself. So this visualization how this kind of canopy glass could look like, so that we are collecting the energy from these metal beams. And then the pattern PV facade panel solution. The product structure is exactly the same as in previous applications, but we cover the whole backside of the glass with epoxy, and we can have color also there, so the architect or designer can play with the black cell shape and the background color in order to create solutions that blend in to architecture. And also we can allow the architects to really integrate the pattern design and cell together. Okay, so we are at the moment in that stage that we have been producing 10 by 10 centimeters working prototypes. The efficiency rate is around 6.5% at the moment. We are able to produce 4 times this size, the 20 by 20 centimeter module very soon. And by the end of this year, we are aiming to get at least 10% efficiency, up to 12%. That is for sure that we are achieving. So that means that if we take 1 square meter area of our panel solution and we cover, let's say, 80% of that with our solar cells, then we can get around 100 peak watt per square meter the power there. We have also studied and made collaboration with engineering company in order to establish the production line setup and also the first calculations that what the actual product cost would then be. It's been quite tricky in that sense that with this technology there is not yet any large-scale manufacturing sites or large manufacturing products available, so there are some questions yet there, but roughly we understand that what is the product cost and of course if compared to Chinese silicon-based cells, the cost is relatively higher, but in this kind of BIPV areas where we actually are producing building envelope components, we believe that our cost per peak watt is really competitive. Okay, that's it.
Thank you very much, Vesa. Do we have any questions for Vesa regarding his presentation or the technology?
Maybe you already explained it, but how do you connect the individual cells together?
They're silver.
So you can't see there's a...
Yes, we like I said, we are aiming that kind of appearance that at least in architectural scale, that is not really visible. So we have thin line and the material that we are is so little that actually it's almost invisible.
And is it actually an applied silver line or?
Yeah.
Yeah.
Yes.
Thank you.
Hi there. Can you do any other color besides the dark colors that you're showing?
At the moment, the black or this kind of very dark brown is the only option with this configuration. So that the color comes with playing with the background color and this cell. So that is how these colored So there is color, but it is between the cells.
I'm sorry, I missed the beginning. What's the active PV material that you're using? Is it perovskite?
Yes.
Okay. Do you have any concerns with silver diffusivity into the perovskite and reacting with the halides?
Okay, I bounce these questions to.
Can I have a quick one?
Yeah.
I noticed the last 2 days during the stages, the carbon footprint is becoming more of importance.
Yes.
Do you have made or performed a calculation analysis? What's the break-even point between production of the BIPV cells and the energy gain? How many years do I need to run these and
The payback
the
time.
carbon footprint?
Well, that kind of calculation has not yet been done. Yes.
Because that might be a question that
Yes.
will arise in future.
Certainly. Yes.
Then you can answer that question.
Can you please repeat that question? It's slipped. Yeah, okay. Yeah, okay. So, okay, yeah, okay. Because our structure is kind of, it is not like that we are evaporating like gold or like silver directly on the whole transporting material or something. It's like we use like carbon as a back contact. So, and then we collect the charges like at the edges or mostly like, but it is not directly coming over the like, the active area. So there is no problem of this kind of ion migration, to the perovskite. I know what you mean. Okay, thank you.
Thanks. Any other questions? Round of applause for Vesa and his presentation. Thank you very much.
Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.